Okay, so the last of the derivatives that we need to know are exponentials and logarithms. Okay, so whether or not you learned that this is really where we look at where the value of e comes from, that it comes from interest theory. So if I have 100% of something plus a little bit more, and that little bit more is 1 over n, what if you partition those little bit mores so that they become infinitely small and you do it infinitely many times? It always comes out to be the number e, which is really interesting. Remember, e is about 2.718. And like pi, it's transcendental. It keeps going on and on. Well, also, in terms of limits in calculus, it is the number that, if you do that number to the h minus 1 all over h, the limit of that goes to 1. Okay? So just looking at the graph, for instance, let's graph e to the x. Remember, it's about 2.718. Okay? So if I make a little t-chart, when x is 0, then it's 1. Okay. When x is 1, the y value is e, so about 2.7-ish. That's about my e. And when x is -1, it's 1 over e, which is about 0.3-ish. Okay. So it's about this. Now, it does have a horizontal asymptote, because no matter what value of x I plug in, it will never ever reach 0, but it can get ridiculously close. And in general, it's going to look like this. Okay, so let's talk about the slopes of it real quick. Let's approximate the derivative. So this is y equals e to the x. And let's see what y prime looks like. So right here at 1, if I were to draw a tangent line, you might notice that the slope is indeed 1. Okay, so it's derivative when x is 1, the slope is 1. Okay. And you can do this as well. Over here where we had it about 1/3, the slope is again about 1/3, so about 0.3. And here at 1, the slope is actually a bit more than 2. It's 2.7. Okay, so it's e. And as we approach a negative infinity, the slope goes closer and closer to 0, but never actually reaches 0. So again, it has a horizontal asymptote. It's kind of interesting, and if you analyze the graphs closely enough, the graph of e to x and its derivative happen to be exactly the same. Okay, so let's prove that real quick. And so we're going to use this limit definition to find the derivative of e to the x. So remember, the limit definition is, the limit is h approaches 0 of f of x plus h minus f of x all over h. I don't even know what just happened there. That is equivalent to the limit, or excuse me, the derivative of f at any point x. Okay, so we're going to do that here. We want to find the derivative of e to the x using the limit definition. So it's going to be the limit as h goes to 0. F of x plus h would be e to the x plus h minus e to the x all over h. Now, we're going to have to play around with a couple little properties of numbers, of exponential functions. For instance, I can rewrite this as e to the x times e to the h, because remember, you add the exponents if they're multiplied and the bases are the same, all over e to the x. And you might notice that I can factor out the e to the x right here. Of course, we don't forget to write our limits every single time. Now that's e to the x multiplied by e to the h minus 1 all over h. And this sucker right here is what I just said, is the definition, comes out to be 1 as the limit as h approaches 0. Okay, it's just by definition that's where e comes from. And so you end up with the limit as h approaches 0 of e to the x times 1. There are no more h's left, and they've all canceled, so it's really just whatever we have left over is e to the x. Essentially, the derivative of e to the x is simply e to the x. By the chain rule, if it's e to the u, and we're taking the derivative with respect to x, remember, it's the same derivative. Remember, it is its own derivative, and then times the derivative of u. So EU times u prime, okay? E to the x is the only non-zero function that is its own derivative, which is very cool and very important. So let's do a practice problem or two. Okay, how about this sucker? F of x equals 2x e to the x plus 3x squared. Note we're going to have to use the product rule right here. And this one just the power, okay? So think of your product as we're going to do f and g, 2x times e to the x. Okay, so it's the derivative of 2x, which is just 2, and then times e to the x, plus the derivative of e to the x, which remember is just e to the x times 2x. And there's your product rule right there. It's super simple. Don't try to overcomplicate the derivative of e to the x. It's literally just e to the x. And now the derivative of 3x squared is 6x. That's it. A couple of times, or every now and then, you might see some other things factored out, such as like this e to the x, but that will not make this any nicer. This would be like a 2 plus 2x and then plus 6x. This is completely fine. Okay, let's do this problem as well. F of x equals e to the 3x plus e to the x squared. Now note, this is no longer just e to the x squared, so of course the chain rule is built in. So think of it as if I have the derivative of e to the u, so you'd have to find the derivative of e to the u part, which is just e to the u, but don't forget to multiply by the derivative of its interior function, okay, so times u prime. So in this case, you'd have e to the 3x, which is just e to the 3x for its own derivative, but now multiply by the derivative of 3x, which is 3, plus the derivative of e to the x squared, which is just e to the x squared, times x squared, derivative of x squared, which is 2x. That's it. I will point out that most commonly the e to the x squared is always at the end, but like it could be 2x e to the x squared, but no biggie. Okay. How about this one? Think of it again as e to the u. This part is your u. Okay, so the derivative with respect to x of e to the u would be u prime e to the u, or the derivative, which is itself, and then times the derivative of the inside. Okay, so f prime of x, everything stays the same. And then, of course, multiply by the derivative of this. Make sure you use parentheses. Ta-da! F of x equals e to the sine x. U is your sine x. So again, e to the u will be e to the u times u prime. Okay, so f prime of x, the e to the sine x, everything remains the same, and then times the derivative of sine x, which is cosine x. All right, so in this case, your u, I know you guys have been struggling with these a little bit, where you've got a bunch of stuff going on inside the chain rule, so we need to do a little bit of practice with these. But, oops, I'm sorry. So again, we're going to do the derivative of e to the x sine x, e to the u would be e to the u and then times u prime. Okay, so it's the u prime that we're going to have to take the derivative of x sine x, and we might have to go off to the side to do that, and that's okay. Okay, so f prime of x, everything stays the same when you take the derivative of e to the x, but now we need to multiply by this bugger. So I'm going to come down here. Let's think, what's the derivative of x sine x going to be? Well, I need to do the product rule here. Make that your f and that your g. So f prime would be 1 times g is sine x, plus g prime would be cosine x, and then times x. Okay, so essentially sine x plus x cosine x. Okay, so that is our u prime. We're going to come back up to where we were, and it would be e to the x sine x, and the derivative of x sine x was sine x plus x cosine x. That is your final derivative. If you need to come off to the side and find that derivative separately, please do. Okay, one more. f of x equals e to the 1 over sine x plus cosine x. It might be helpful to rewrite this as e to the sine x plus cosine x to the negative 1. So you can see here when we take the derivative of this, of course, we're going to have to use the chain rule itself just for the derivative of the exponent part. Okay, now otherwise you would use the quotient, which you're welcome to. Remember, the derivative of 1 is 0, and you don't want that to get in your way. So this little bugger right here is going to be our u. So then when we take the derivative of e to the u, it'll be e to the u and then times u prime. Okay, and again, we're going to come off to the side and take that derivative. I'm sorry. Okay, anyway, so this will be e to the sine x plus cosine x all to the negative 1. Now, we need to multiply by our u prime right here. So I'm going to come off to the side, like I said. We need to find the derivative sine x plus cosine x all to the negative 1. Okay, so take the derivative of, this is like a chain rule here. Take the derivative of our outside. We've got u to the negative 1, which will leave us with negative 1, u to the negative 2, but don't forget to multiply by u prime. So the derivative of sine x, the derivative of the outside would be a negative 1 times sine x plus cosine x all to the negative 2, and then times the derivative of the interior, sine x plus cosine x times cosine x, and then don't forget the derivative of cosine is a negative sign. So all of this fancy stuff goes there. Okay, so we already took the derivative of e to the u, and so now we just need our u prime. So it'll be times a negative sine x plus cosine x all over to the negative 2, which keep in mind this is the same as just putting it all in the denominator and squared, and then times cosine x minus sine x. Okay, and of course you do not have to simplify unless you're using it for something, and we are not. All right, one last question in this second. Find the 37th derivative of x e to the x. So I'm sure as you're guessing, this will be just like finding the derivative, 37th derivative, for instance, of sine of x or cosine of x. We're going to go all the way down. So we're going to have to use the product rule here. So let's start with our first derivative. And remember, you want to keep going until you see a pattern, and you're like, well, duh, this is what it's going to be. Okay. So f prime would be 1 times e to the x plus g prime would be e to the x and then times x. What's really cool about stuff with e to the x in it, when you take the derivatives, a lot of times you'll see the original function appear back in its own derivative. Okay, so one thing I want to point out here is if I factor out an e to the x, I'd have a 1 plus x left over. So that's for our first derivative. I'm going to kind of mark that here. Derivative 1 is e to the x times 1 plus x. Well, let's find our second derivative. The derivative of e to the x is just e to the x. Now, notice I've already taken this derivative. It came out to be the whole thing. We found that if you took the derivative of x e to the x, you would get e to the x plus x e to the x. Which is kind of neat. So I have that right there. So I know that's the product rule, and you're welcome to do it again. But you get e to the x plus x e to the x. Well, I've got two of these. 2 e to the x plus x e to the x. And just so you can start to see a pattern, I'm going to factor out that e to the x again. So I'd get e to the x and then 2 plus x. That's my second derivative. Well, it looks like there's a pattern here. Let's see if that's consistent with our third derivative. In math, you always want to make sure if you're going to hypothesize a pattern that you at least go one or two or several iterations to prove that. Okay, so I'm going to go one more iteration. Take the derivative of this sucker, be 2 e to the x. And again, we know that this is the derivative of x e to the x. It's e to the x plus x e to the x. Okay, and so there's 3 of the e to the x's, and then always an x e to the x left over. Factoring out that e to the x indeed leaves us with 3 plus x. So think about what's happening here. We're gaining an e to the x every single time. And that's what this is saying. If I take the derivative of x e to the x, I always gain one more e to the x. So one could hypothesize for the nth derivative, it should be e to the x n plus x. Okay, and so for a 37th derivative, I hope you see that it would be e to the x times 37 plus x. Okay, so just to make the video short, this is the first video on the derivative of e to the x, and the next one will be on the derivative of any base.